Okay, hi everybody. We're here today to save you from an unspeakable evil. But before we tell you what it is and how to protect yourselves, let us tell you a little bit about who we are. So my name is Alex. I live in New Jersey with my amazing wife and 3 children, who were very gracious to let me cross the pond for a couple of days by myself. And I work at Capital One. I help maintain a machine learning platform internally. I'm also a Kubeflow member and contributor, and I'm deeply honored to be here today as a speaker, and I'm also honored to be sharing the stage with Murthy.
Thank you, Alex. Hi, everyone. My name is Murthy. I work as a distinguished engineer in Capital One. I'm passionate about open source, Kubernetes, building platforms, and related services. I also come from New York City, and I live in New Jersey again, along with my amazing wife and 2 kids. It is exciting, and I'm feeling great to be here to present this topic, along with Alex, who is a true subject matter expert in this area.
Thank you, Murthy. So as I was saying, we're here to protect you from an unspeakable evil. If I could add an ominous sound effect to this slide, I would, but you'll just have to use your imagination. If you're not familiar with this acronym, congratulations, may you never see the horrors that we've borne witness to. NIH stands for Not Invented Here, and it's basically when companies decide to roll their own solutions instead of leveraging mature, industry-standard, widely adopted open source solutions. To be clear, there are specific use cases where it makes sense to build versus buy, or whatever the open source equivalent of that is, I guess, build versus don't buy. So a little context on this image here. We're not allowed to use unlicensed images in our deck. So in the spirit of malicious compliance, I asked my children, and Murthy asked his children, to illustrate some of the memes we wanted to use. So you'll see sprinkled throughout this presentation some drawings. And if you're not familiar with this, this is from Monty Python and the Holy Grail. It's one of the knights who say Ni. I don't know how to pronounce NIH, but I'm just going to call it Ni from now on. So kudos to our children for helping us out. So story time. At one of my earliest jobs within the industry, I was tasked with maintaining an in-house version of Terraform implemented in Ruby of all things. And it was kind of a nightmare. And on some level, the rest of my career since then has been a kind of prolonged, horrified recoil to that experience. At some point, I asked for advice about this tool in a Slack workspace for DevOps engineers, and I was told to, quote, find a new job immediately. Thank you, brutally honest stranger on the internet. I actually listened to this advice. It was good advice. So the point I'm trying to make is, for the love of all that is good and holy, please, please, please resist the allure of NIH and use industry standard open source software instead. But you guys all know this. I mean, this is a sophisticated audience. We're at KubeCon. There's just one problem: capability gaps. So when you work in a regulated industry like we do, where there are elevated security requirements and regulatory requirements, sometimes you can't just use the open source software that you want to use off the shelf. And that's because it doesn't meet specific internal mandates. Now, when you find yourself in this situation, you're kind of at a crossroad. If you enjoy making people suffer, you can use those capability gaps as a justification to reinvent the wheel. If you're not a Sith Lord, you can close those capability gaps in your open source dependencies. So to give you a sense of the kind of capability gaps we're talking about, here's a list. I'm not going to read them off to you, but these are things that we've dealt with or similar to things that we've dealt with. And it's not an exhaustive list. But the point is that the lift of reinventing the wheel is almost always going to be greater than the lift of closing these gaps in your dependencies. So today we're going to talk about 4 different ways to address these capability gaps in your open source dependencies: contribution, forking, wrapping, and mutation. We're going to kind of breeze through the first 3 because the 4th is kind of the most novel. So here we go. So for each approach, we're going to provide an example. We're going to delineate the pros as well as the cons, and we're going to conclude with a kind of comparison matrix as well as a decision tree to help you evaluate which specific solution to use for your specific use case. Let's start with my favorite, contribution. So we do a lot of this. I'm a Kubeflow contributor and member. This is honestly my favorite part of my job, and it's always the go-to solution for us, unless there are kind of obstacles to leveraging it, which we'll talk about in a second. The advantages are pretty self-explanatory to an audience like you guys, so just to breeze through them quickly. Essentially, when you contribute, you're distributing the maintenance burden across a worldwide network of software engineers. And that's incredible, and it's hard to compete with. On some level, for most companies, if you are not open sourcing, you're kind of dead in the water. And here's why. Contributor count. Unless you have a team of almost 4,000 engineers to maintain this internal product that you want to build, it's going to be very hard to compete with something like this. Now, granted, on some level, Kubernetes is kind of at the end of the bell curve, but you get the idea. The question is, do you really want to step into the ring with something like this? The point is, don't compete, collaborate. In addition, and this is also pretty self-explanatory, but when you contribute to open source, you broaden your impact. You're not just solving a problem that's internal to your company, you're solving a problem that's global, potentially. And of course, community. Just look around this room. None of us would be here if we only worked on internal products. And it's a real privilege to collaborate with people from all over the world and learn from them and develop your craft and develop friendships. And you don't really get that when you're stuck in NIH. So I'm not sure I'm allowed to present this slide here at KubeCon, but in the spirit of honesty and transparency, I do feel obligated to. So there are some drawbacks to bear in mind with contribution. First and foremost, and most of the time when we're not contributing, this is the obstacle that's preventing us from contributing, and that is that proprietary functionality cannot be contributed. To some extent, you can offset this when you have pluggable architecture. You can inject functionality at runtime, but not all projects support that. And in addition, contribution requires patience because you're kind of at the mercy of the maintainers who have competing priorities to review your code, to merge your code, to cut a release. And if you need something immediately, contribution might not be the solution for you in the short term, although you can always loop back around and contribute the solution later. So let's move on to the next approach, and that is forking, or as some like to call it, dingle hopping. So a fork is basically when you make a copy of existing code and provide changes on top of that. There are plenty of notable forks in the wild, such as Valky, OpenTofu, and less notably, our internal fork of the Kubeflow Pipelines UI. And the primary advantage of a fork is that you have total control over the code base. You're not at the mercy of maintainers. You don't need anybody externally to review, merge, and release your code. What happens between you and your fork is none of my business. This allows you to, among other things, incorporate complex business logic. And as mentioned, it also expedites delivery. That being said, those are appealing advantages, but there are significant disadvantages that you need to take into consideration. First and foremost, high maintenance burden. You're not distributing that operational overhead. You're now responsible for this code that you have total control over. And often that results in upgrade friction. When you need to rebase changes from the upstream origin into your fork, you'll often wind up with merge conflicts. And that kind of results in feature lag, where if you have an internal fork, there might be functionality that's enabled in the upstream that you haven't had a chance to pull downstream, and so your internal users can't benefit from that until you go through the upgrade friction and pull in that functionality. There are some things you can do to offset these disadvantages. First and foremost, keep your fork as small as possible. Try to consolidate it and keep the surface area as small as you can. And secondly, you can kind of treat your fork as like a staging ground for open source contribution. There's a bit of a revolving door between these different solutions. So you can start with the fork, and then for example, address something that needs to be addressed immediately. And then you can ultimately contribute that functionality upstream and thereby remove it from your fork and reduce the surface area of your fork, and then reduce the operational overhead of maintaining your fork. Now let's move on to our third solution, wrapping. So a wrapper is essentially where you abstract underlying dependencies, and you can be deliberate about that. You can deliberately obfuscate them, or you can be transparent about your dependencies. The wrapper can happen server-side, or it can happen client-side. A good example of a wrapper that we use on a regular basis is Kubeflow pipelines. So Kubeflow pipelines wraps both Argo Workflows as well as Tekton. Each of those are workflow orchestration engines, and Kubeflow pipelines is kind of a more machine learning focused workflow orchestration engine. And that's the additional functionality that it adds on top of the things that it wraps. But ultimately, it is a wrapper and an abstraction on top of those two tools. So wrappers, like forks, allow you to incorporate complex business logic. And unlike forks, they allow you to obfuscate the underlying dependencies. Among other things, this protects against volatility. If an underlying dependency changes in some way that no longer meets your requirements, let's say, for example, it changes its license or something to that effect, in theory, because you have a wrapper, you can swap out that offending dependency without directly impacting end users. And in addition, it results in interface control. So you can completely redefine the user interface, whether it's an API, CLI, a GUI, or an SDK. Kubeflow Pipelines does this with Argo Workflows, and this is just to give you a sense of how it's kind of rebranding the underlying functionality, providing a unique conceptual framework, unique nomenclature, but under the hood, when you quote unquote compile a Kubeflow pipeline, you're winding up with these underlying Argo Workflow abstractions, with the exception of the cron workflow. So all of that sounds lovely, right? But wrappers have massive, massive disadvantages. And I think sometimes people fail to take those into account. So first of all, just like forking, you have high maintenance burden, upgrade friction, feature lag. And in addition, what I found is that people who maintain wrappers, oftentimes engineering time and effort is redirected away from feature delivery for end users and towards wrapping tracked targets. Because it's not a trivial task, especially when you're targeting multiple complex underlying dependencies, like, for example, the way Kubeflow does with both Tekton and Argo Workflows. In addition, wrappers result in increased complexity, and that translates into brittleness and difficulty when debugging. So, for example, when a Kubeflow pipeline run fails, we have to kind of determine if the issue is end user code, Kubeflow pipelines, Argo Workflows, Kubernetes, or something lower in the stack. Any one of those individually is enormously complex and difficult to debug on its own. When you combine all of that together, it's hard to kind of sift through all of these abstraction layers to figure out what the exact source of the problem is. And this one's interesting because it was also listed as a pro, but proprietary interfaces result in something that I personally refer to as cursed knowledge. And what that means is, as engineers, we want to invest in skills that are transferable to the next role that we find ourselves in. And when you're forced to work on proprietary interfaces that don't exist externally, you're developing expertise and skills that aren't transferable, and that can be kind of frustrating. I find that maintainers and end users are a lot happier when they're able to invest in industry standard interfaces. So I'm going to hand it off to Murthy now to talk about what I think is the most novel of the four approaches.
Thank you, Alex. OK, let's start on mutation. Before we start on mutation, let me start small intro. Okay? In Kubernetes world, mutation means you're modifying the manifest at the runtime or on the fly before it is actually created within the cluster. How it works, for example, when user is submitting some manifest or some application is creating some manifest in the cluster, the request sent to API server, the API sends the HTTP calls to the corresponding webhooks. The corresponding webhooks matches a target and it takes action like modifying or something. Then again it sends the call back to the API server, then the API server creates a manifest. In a high level, this is what happening behind mutation. Okay, how mutation is helping in this context? As you can see in the slide, without mutation, you're actually touching the source code of the application. For each application, for example, pipeline or Argo Workflows or Catty, whatever the open source application, you're touching the code, you're making the changes, you're maintaining it internally, or you're creating wrappers out of it. That comes with the high maintenance, right? With mutation, you're not touching the source code of open source repos at all. You're directly modifying the manifest. In that way, it embraces a common approach. You don't have to worry about what language it is written and all those things and all. You're directly working in the middle layer, one level up. For the purpose of this session, we will go through Kyverno. Before we start on Kyverno, There are general purpose mutation webhooks or admission controllers available, like OPA is one of the example, Kyverno is another example. There are application specific webhooks also available. If we all know Istio, Istio is having its own kind of mutating controller to inject sidecars and other things. Or you can write your custom webhooks also. Suppose if you're writing some application, you can write a custom webhooks also. But when there is a general purpose thing is available, then you don't have to write a custom webhook. That is what we are going to see today, one of the example. And Kyverno is a open source general, where Kyverno lands in this area, right? Kyverno is a open source general purpose admission controller. It is a YAML-based policy engine. It is CNCF in incubation. I think it got it in 2022. It's a general purpose one, so you can. It's simple, powerful. It's YAML-based. You don't have to learn any language, any specific language. For example, a Rego language similar to for open. Those things, it's all YAML-based with Kyverno. It can do all the actions. That it can do It can validate your manifest. It can mutate your manifest. It can create resources. It can delete resources. It can do all set of jobs for you. It can talk to API server. It can get some values. It's simple and so powerful in a nutshell. Okay, you can read your metadata values from namespace. It can talk to API server. It can get additional values so that you can use the values to mutate your manifest. Let's see, okay, how this mutation validation is working with Kyverno. On a high level, Kyverno is working based on policies. This is a YAML-based one again. You have two kind of policies. One is cluster level policy, where you can apply at the cluster level, you can create a rule that is applicable for all the namespaces. Then the next one is a namespace specific policy, as name suggests, so it is applicable only within the namespace. Within each policy, you have a set of rules, like you can have multiple rules. In one rule, you can say, hey, inject environment variable. In the other rule, you can say, okay, inject volumes. You can take multiple actions under a single policy. Basically, you can nest. Then the match section or exclude section comes. It is where you define the targets. Okay, I want the action to go on a namespace. I want the action to go on a pod. So all the match, all the targets you can see on the right-hand side. You can do pod level. You can do it on a specific objects like with the names, labels, annotation. You have all these kind of options to set your targets. In the bottom section, you have all the actions. You can do validate, you can do mutate, generate is nothing but create resources. Then the last one is a verify images. That is kind of alpha or beta. Basically, you can verify your image checksums. Let's see how Kyverno is implementing all these operations behind the scene. Let's go through some high-level architecture. This is the high-level architecture behind Kyverno. Most of the thing is internal to Kyverno. I will just go through three main controllers. One is admission controller, which is responsible for your validation webhooks and mutation on the new resources. The background controller is for your create resources objects, create resources operations, and for mutate on the existing objects. Then there is a cleanup controller that is responsible for your cleanup. Basically, you can delete resources also on user namespaces and those things. Other things are all very internal to Kyverno, so like said, webhook controller, set renewer, and everything, how it handles the operation behind the scenes. I have to say this. We are not vendor, we are not selling Kyverno, or we are not promoting anything here. We are also users. This is a easy general purpose admission webhook available there. So we just want to see, so you can all, how easy and powerful it is to do the mutation. Sorry for the picture. I have requested my kid to draw a stop sign for me. She was really making sure it is a stop sign. Okay. Yeah, thank you. Okay, let's go through some examples, okay? Like common examples where everyone goes through. This is a common one. In an enterprise and regulated environments, they don't allow the public like image repos, right? So then you have to mutate those manifests to reflect into internal repos. This is one of the sample policy that you can use. You can match the image, then you can replace it with your internal artifactory. We face this issue in one of the Kubeflow pipelines things where user don't set the default image, then it pulls, it's tried to pull Docker image from docker.io, which never works in our environment. So we use this policy to effect, okay, do it on the fly, even user don't specify it, you mutate it so that it don't break their pipelines. Then this is another one we all go through, right? And I think same, in a regulated environments, they want you to explicitly define the security context, what is the user ID for the container, set allow provisional escalation to false, and various settings under the security context, right? You can use as an example to set it actually. I think one of the examples, I think we were facing issues with cat team. They were creating suggestion deployment or something inside, then where we were not able, because basically they were hard coding it. We were not able to do it. So our only solution, either you fork it, modify it, deploy it inside, or we use, but in that case we used mutation webhook. Okay, we can modify it on the fly. In that way we avoided the forking. As you can see, you have a rules under, like this is a single rule application. We want to keep it simple. That is why you see a single rule. You see a target. Okay, it is targeting parts. It is targeting a namespace with a Kubeflow profile label on it. Then it sets a precondition. The image should be like within this one. Then finally you are making the action. The Kyverno is not just working based on native Kubernetes resources. This is an example of how you can extend the mutation to custom resources. Dask is one of the custom resources. Basically, you can define any resources, not just Kubernetes native resources. You can use custom resources also. This is a problem where this is another example where you can enforce some behavior on user. If you use, through this example, what we did is we enforced, okay, your maximum idle timeout is 1 hour. In that way, you are enforcing the user behavior, so all the objects will be deleted after like 1 hour of timeout in Dask job. That resulted in saving a lot of money for us. And this, yeah, so we all come across problems, right? So we run notebooks, for example. We run long-running jobs like XGBoost. The part does not, so basically Kubernetes should not disturb those parts, correct? Like, so if they disturb those parts, then whatever job is running, that will get disturbed. It cannot afford part disruption, right? In a Kubernetes world, the carpenter or any cluster autoscaler, that will try to reschedule the pod in a better node to improve the node usage, correct? But these long-running job parts, they cannot afford this kind of a pod disruption. You can use this policy in example, or we use this policy in example to protect those parts. So we did apply this carpenter annotations on notebook parts, in the XGBoost parts, so that our long-running jobs were protected. And this is an example of sidecar containers. So when you're developing, you don't have to develop like a custom webhook when you're developing internal applications. You can think of like a Kubeflow notebook is having its own admission webhook, Istio is having its own admission webhooks for them to inject like a sidecar or any other operation. Suppose if you're developing something internally, and I think if you all know, like sidecar containers are very famous in Kubernetes. It can abstract a lot of logic from main containers. For example, metrics collection, orchestration, storage injection. You can name anything. You can achieve it through Kubernetes sidecar containers. You can use this policy in example how you can inject sidecar containers into your workloads. As you can see, you're not just injecting the containers, you can also inject configurations along with it. In this example, you are injecting environment variable, you are injecting security contents, you are injecting volumes, you are injecting volumes. Basically, you can draft everything or you can dictate everything along with your sidecar containers. That is why it is so powerful. And in the bottom section, it says precondition. So you can literally tell Kubernetes, hey, don't touch any existing objects. Okay, do it only on the new objects. So you can define all those conditions also here. Let's move on to some validation policies. In a multi-tenant environment, there was always a requirement. Right? We want to track which namespace belong to which team, which project, and all those things. And we want to deny those objects which is not meeting the requirements. We can use this policy in an example to, okay, don't create namespaces or don't allow namespaces which is not having a project name or T name. In that way, your Kubernetes resources are compliant enough. In this example, is a general practice, right? So the node scaling and everything, like cluster, whether it is a cluster autoscaler or carpenter, they all work based on your container requests. It's a general practice in Kubernetes to keep your limits and request difference ratio within 20%. Correct? How do you enforce it? Because some containers we may be creating, some containers user may be creating, some containers may come from open source. We can use this as a policy to enforce the behavior. Okay, if you're not meeting this criteria, if your request and limit ratio is not within that 20%, I'm going to deny the pod creation. You can use this, and we can use this as an example. And this is an example for a create policy. So we were writing wrappers, okay, before we adapt Kyverno and all, right? So we were writing wrappers. You may come across some situation, a multi-tenant platform situation, you want to give them a basic volume, like, hey, I'm giving you a workspace volume, where you can put all your data inside. We will not let you to create volumes because it is going to cost a lot of money, correct? You can use this as a policy and example to create those default volumes inside user namespaces. Basically, you can avoid wrapping to input those kind of a logics with this kind of a policy. Let's see some deletion examples, correct? Same story, like in your dev environment, if people are I'm again sticking with a basic example. In a dev environment, people can create volumes. There will be like orphaned volumes, and we don't want platform admins, or you don't want platform admins to go and manually check, okay, how old it is, delete and all those things, correct? You can use this policy to an effect. Hey, if the volume is 1 month old in a dev environment, you can automatically clean those volumes. In that way, you will save a lot of money. In the deletion of stale resources, you can achieve it in 2 ways. One is through policy, as we've seen like through YAML, or you can just inject the label, the cleanup.kyverno.io/ttl, 30 days. Okay, so the Kyverno controller will watch for this label. It will delete all your stale resources automatically. Quick question: how do you inject these labels automatically into like user workloads? Mutation, correct? So you can mutate this thing whenever somebody is creating a volume. You can mutate, or whenever, and same can be extended to your ingress also, right? You can delete the load balances. You can save a lot of money. You can extend this label to any objects which users are creating. In that way, you delete the stale resources, you do the garbage collection, you save a lot of money. Sorry for the picture again. I'm requesting my kid to write a cloud, sir, draw a cloud. Do you need more? She drew the cloud. She was making sure it is a cloud. Okay. And whatever we have gone through, it is very basic examples, okay? Yeah, but Kyverno is so powerful. As I said, like you can directly read from Kubernetes API server. You can read from your namespace for some data. Like for example, if you want to automatically propagate IAM role from a namespace to underlying parts, you can propagate. Or you want to read something else from API server, you can do. There is a repo here. I don't know what is the exact number, but at least it contains like hundreds of examples there. You can take this as like a reference. You can create your own policies to match the requirements, to match your requirements. Let's see some of the pros, right? It is easy as hell. You're not learning any code or anything. You're working on one level up, or you're working directly on the manifest. There is no maintenance burden. You don't have to fork, or you don't have to wrap individual repos. You don't have to do anything of that kind. And you're embracing the common solution. You're not working on the individual open source project level. You're addressing cluster as a whole, or your platform as a whole. And it comes also with like a little bit mutation cons actually. Because it is mutating those manifests at the runtime, it comes with a computational overhead because it intercepts every API request. It comes with its own computational overhead. But there are ways to address it. Okay, it supports Kyverno supports high availability. You can run like multiple replicas. There is a busting capacity and all that you can increase. Please, you can refine your Kyverno implementation based on the scale of your platform. Then the next one is mutation errors. Because the error, if something happens, the error is not reflected in application containers. The error will be reflected in Kyverno controller. So you have to rely on your platform admin to debug, okay, what has gone wrong, why this is not working. So that is one of the cons. But these are all, compared to other cons, these are something we can solve it with. With that, I'll hand over it to Alex to go through the final slides. Thank you, everyone.
Thank you, Murthy. So here's a fancy table. And the main thing we want you to take away from this is, first of all, there's no one solution fits all problems. Your specific use case might mandate one versus the other. But also, you probably want to move between different solutions. So you might start with a fork, and then when there's less urgency, work on a contribution. When that gets merged, you can eliminate the fork. And same applies for mutation. You should periodically go through your Kyverno policies and see if A, those holes have been closed in the upstream dependencies, or if you want to contribute so that you no longer have to maintain that policy. We created this decision tree to kind of help you digest that last table. And basically, we'll walk through it. Is the solution proprietary? If the answer is yes, then you can't contribute, so that rules contribution out. Is the solution urgent? If the answer is yes, then you can't contribute unless you personally know the maintainers and they can expedite the merge and release for you. So in either case, you wind up at, can you mutate? If you can, that's probably a good solution, just because the maintenance burden is so low. And then if you can't mutate, then you have to ask yourself, do you want to abstract the underlying dependency? And if the answer is yes, then go ahead and wrap. And if the answer is no, then fork. And again, remember, you're moving through these different leaf nodes here. So, what we want you guys to take away is that it's worthwhile to close these gaps in the upstream instead of rebuilding stuff in-house. And there are short-term solutions to help you avoid NIH as well. And just some high-level takeaways. Like I said, avoid NIH like the plague. Contribution is the ideal solution if you can make that work. Mutation is awesome. Don't fork unless necessary, and keep your forks small. Unfortunately, there wasn't like a fork-only emoji, so you just have to ignore that knife over there. And only wrap if the cost is justified. So that concludes our talk. I want to thank you guys for attending, and I also want to thank our esteemed but nevertheless unpaid illustrators. We compensate them in other ways. Thanks, everyone.
Thank you, everyone. Thank you.
Do we have time for questions? I'll stay up here until somebody kicks us off.
We will step aside. If
questions?
there is any questions, you can walk over as well.
Or you could come.
Thank you,
come over.
Yeah.
We're happy to talk to you. Thanks, everyone.
Thank you, everyone.